Let's go back to our normal distribution. A continuous random variable like x is said to have a normal distribution with parameters mu and sigma, where mu, or the population mean, bounded between negative infinity to infinity, and sigma is positive. If the probability density function of this variable is f of x with parameters mu and sigma, which is 1, divided by square root of 2 pi times sigma times the exponential function e to power negative x minus mu squared divided by 2 sigma squared. Remember that if you use z instead of x, you define standard normal distribution. For a standard normal distribution, as you remember, mean is 0 and standard deviation is equal to 1. So if we do the substitution, you can write the probability density function for z as f of z, 0 and 1. Again, mean is 0, standard deviation is 1, and it is 1 divided by square root of 2 pi, but sigma is equal to 1, so it disappears, times, if you simplify the exponent, you get e to power negative z squared divided by 2. Well, as you remember, the cumulative distribution function of z is the probability that z is less than or equals to z, or the integral of f of y dy, y ranges between negative infinity to z. Now we want to calculate the expected value and variance for this type of variables. Remember, if x is continuous random variable, the expected value is the integral of x times f of x, and then we just need to do the calculation. We are going back to calculus. We defined the PDF, or probability density function of x, as 1 divided by square root of 2 pi sigma e to power negative x minus mu to the second divided by 2 sigma squared. Now, the expected value of x is 1 divided by square root of 2 pi sigma. Please note that this is just a number, so that's why you can write it in front of the integral. And the integral of x, the exponential function dx. To make this integral a little bit more manageable, we're going to write x as x minus mu. Very good. So let's see what's happening here. The expected value of x becomes mu times 1 over square root of 2 pi sigma times the integral of x minus mu e to power negative x minus mu to the second power divided by 2 sigma squared dx. Now, the rest of the integral can be written as mu times 1 over square root of 2 pi sigma times the integral of e to power negative x minus mu to the second divided by 2 sigma squared dx. Let us make it more easier to read by using a nice substitution. Wherever we see x minus mu, we're going to use y, so we can analyze the first integral a little bit better. So when you write x minus mu to be y, the first integral becomes 1 over square root of 2 pi sigma, the integral of y times e to power negative y squared divided by 2 sigma squared. So here, x minus mu is written as y, and then up here on the exponent, you also get a y. So basically, as you can see, you have an odd function inside the integral and you have symmetry. It means that the first integral we expect to be 0. Plus mu times the integral of f of x dx. F is the normal density function. So the first integral becomes 0. And the second integral is mu times 1. So you get mu back. So again, remember that the integral of f of x, when x ranges between negative infinity to infinity, is the area below the curve, which is 100% or 1. So you have 1 times mu, which is mu. So let us analyze the first integral a little bit better. The first integral, when you write it as y e to power negative y squared divided by 2 sigma squared, follows this behavior. So as you can see, here you have an odd function, and it is symmetric on negative infinity to positive infinity. You have negative infinity to infinity as the domain, so an odd function over this domain has integral 0. Again, y is odd, and then when you multiply y by an even function, which is this exponential function, the result is also odd function. You have an odd function over negative infinity to infinity. You have a symmetric interval, so the integral becomes 0. Here's more detail for you. For those of you who are curious in analyzing the integral, you have this. So far we calculated the expected value. Now we are interested in knowing what is the variance for a normal distribution. Here you have your probability density function for a normal distribution, and we calculated the expected value to be mu. So when we're calculating the variance of x from the formula, as we learned before, it is the expected value of x minus mu to the second power. So basically you have 1 divided by square root of 2 pi sigma, the integral of x minus mu to the second power times the exponential function e to power negative x minus mu to the second divided by 2 sigma squared. We are taking the integral with respect to x. Please note that if you use a substitution like y equals to x minus mu divided by sigma, this integral can be written a little bit nicely. You get sigma squared divided by square root of 2 pi times the integral of y squared e to negative y squared divided by 2 dy. Why we write it this way? Because now you can easily see that you can apply integration by parts and take this integral. Integration by parts, u is equal to y, dv is y e to power negative y squared divided by 2 dy. So you have uv minus integral v du. So sigma squared divided by square root of 2 pi times uv, which is negative y, e to power negative y squared divided by 2, plus the integral of e to power negative y squared divided by 2 dy. The very first term here is just 0. If I plug in infinity, I get 0 back. If I plug in negative infinity, again, I get 0 back. So this quantity is 0. The only thing we need is calculating the second integral. We want to show that this is equal to sigma divided by square root of 2 pi times this integral, which becomes sigma squared. How we do this calculation? Let us go to the next page and show you what to do. I'm rewriting what we had on the previous page using integration by parts. This is what we have, and we know that this quantity is 0. Just basically plug in infinity. Since you have negative exponent, this guy goes on the denominator, and you have negative y divided by e to power y squared divided by 2. You get infinity on the denominator, which is 0. You get infinity on the denominator for negative infinity, which is 0 again. So you just need to calculate the rest of it and show that it is equal to sigma squared. How are we going to do the calculation? To do the calculation, we want to use the Gaussian integral. The Gaussian integral says, well, the integral of e to power negative u squared du when u ranges between negative infinity to infinity square root of pi. Now, you're going to use the Gaussian integral and show that the integral of e to power negative x squared divided by 2 dx is indeed square root of 2 pi. To show this, we're going to do a little bit of substitution. Let u be x divided by square root of 2. Du is 1 over square root of 2 dx. So dx is square root of 2 du. So your integral of e to power negative x squared divided by 2 dx becomes the integral of negative u squared times square root of 2 du, which basically is square root of 2 times the integral of e to power negative u squared du, which is square root of 2 times square root of pi, or square root of 2 pi. So we just calculated the integral here. The integral of negative e to power negative x squared divided by 2 dx is square root of 2 pi. This is this integral on this side. So you can basically cancel out the integral and square root of 2 pi because they are the same thing. One on the numerator, one on the denominator. Sigma squared is left. So the variance for a normal distribution is sigma squared for your continuous random variable x following a normal distribution. So try to feel comfortable about these kinds of proof, going back to elementary calculus, doing integrations, and so on.